So now I'm going to tell you about orthogonal projections. This is related to the idea I have mentioned before, which is a key concept behind the dot product, and that is that it allows you to give you a sense of how much information two vectors share among themselves. In other words, the dot product allows you to compute the shadow of one vector along the other, which is more formally known, more technically known as the orthogonal projection. So the idea is that it's better just to do some pictures first to see what we have in mind. So imagine that you have a vector v, a vector u. So we want to compute the shadow that v makes along u, which will correspond to this piece. And this piece will be denoted the projection of v along u. Okay? So you should think of this as a fancy name for a new vector. Now, really, you should think that u determines a line, okay? And this projection this is like the shadow of v along u, but in reality this shadow only depends on the line determined by the vector u. So what I mean by that is that, for example, imagine that you shrink this vector u a lot. So I shrank u, but still it determines the same line as before, okay? Right? You still have the same line, and hence the orthogonal projection or the shadow will be the same exact vector. So it will be still projection of v along u. Okay? And you could even do something more extreme, which is take the same vector v, and now let's just reverse the sign of u. I mean, now this is, I should call this u1, maybe. No, let's call this u still. Now call this w, and let's call this, well, let's create a letter, a new letter. Or maybe creating a new letter is not a good idea. Let's go back to u, v, w, a. Let's go back to the beginning of the alphabet. So, so what I was saying is that this projection is the same as the one before. And in this case, the projection, again, this vector A determines the same line as v and w, and hence the orthogonal projection, which is the shadow, continues to be the same. So that's why what I mean by saying that the projection only depends on the line. And then, really, once we know this fact, finding the formula for the it's easiest to find the formula for the orthogonal projection from this version, just psychologically speaking. So let me just go back to this side. So essentially, remember that that's why in the previous video I talked about unit vectors. For any vector, there's like a normalization or a canonical version of itself, which is the unit vector. So we have here a unit vector which is called, let's call it E sub u. Remember that E sub u was just a vector u divided by its norm. And basically what you should think is that you should think of this projection as just stretching this unit vector by some factor. So you should think of this projection as some factor lambda times the unit vector E sub u. And this is, you should just think of this as some stretching factor. And what is this factor? Well, we just have to apply basic geometry to figure it out. You have a right triangle here, right? So let me just do the picture again. This is the line determined by u. We have this vector v, which has some norm or size. Now we just care about the sizes. So it has this hypotenuse has size norm of v. You have this right angle, and then you have this psi, which is the norm of the projection. And so by basic trigonometry, right, the cosine of this angle, theta, right, what is the cosine of theta? Well, that's the adjacent side, which is the norm of this projection, divided by the hypotenuse, which is this. But remember that there's like a formula for the cosine of the angle using the dot product, and this is where the dot product appears. And this was just u dot v divided by the norm of u times the norm of v. So you get this. And you see the norm of v appears on both sides, so we can cancel it. And so we find the formula that tells you that the size of the projection and this is key, is just u dot v over norm of u. Okay? And why is this important? Because if you compare this with this formula, I'm writing the projection as some constant times a unit vector. This is precisely the same as the polar decomposition that I mentioned on the previous video. So this lambda is really nothing but this side, this magnitude. And so the key formula that we just found is that the projection of V along U is just lambda, which is U dot V over norm of U, times a unit vector along U, which is U over norm of U. Okay? So in the next video, I'll do an example, a couple of examples with this formula and tell you a little bit more about it.